session of this last afternoon of this conference. We have 4 talks, 2 and 2, and the first talk this afternoon is by Boris Pavlov, with a double affiliation. One is St. Petersburg and one is, what is that, Auckland, New Zealand, and the title you see here. So Boris, please.
This talk, thank you for organizing my talk here. It was a pleasure to come again to Cambridge. So now the motivation of this talk is physical, and Professor Bagraev is very well known experimentalist in Silicon area. Gavin Martin is my friend. Oh. Thank you. Gavin Martin is my friend and collaborator in my institute in New Zealand. And extended version of this talk was recently presented by my student on some physical conference in France. So I will try to keep in the mathematical direction of this area. So first of all, I wish to motivate why it is connected with quantum graphs or quantum networks. We had here several talks discussing the boundary conditions at the vertices. Usually in these talks, the authors consider the limit process when the vertex domain with few leads somehow is either constant or slowly shrinking, and the width delta goes to 0 faster. My assumptions are slightly different. Nothing goes to 0. I just have 2 important parameters. I have Fermi level or the renormalized Fermi level, which defines exactly the energy of moving electrons or holes in the semiconductor at 0 absolute temperature. So this is. Then, of course, I need delta, and I need temperature. So actually, I consider a local version of spectral problem on a given interval of energy, and the size of the interval depends on the temperature. It is slightly different from what was discussed here. But it is exactly what my friends physicists who need my help wanted me to concentrate on. Then, what was the physical motivation here? The physical motivation appeared when Professor Bagraev attended some conference on graphene. You know what is graphene, and usually you see the picture of a hexagonal lattice with few cones, and these cones are drawn here to show that the effective electron mass on this lattice is 0, so the electrons is moving in quasi-relativistic way on this lattice. Then, when attending the conference, Bargraev formulated for himself a question: if the special behavior of charge carriers in graphene can be somehow observed in other materials. Graphene is extremely interesting material, but not only where we can expect this property. And Bargraev is a very sharp experimentalist in silicon area, and he discovered the following phenomenon. He constructed a sandwich of 3 layers, silicon inside, and 2 layers of silicon plus borons on both sides of it. Then, so these 2 layers are doped with borons, and the doping is practically periodical. So there are 2 atoms of borons forming dipoles. They form a periodic lattice in the upper layer and in the lower layer. And Bargraev observed very special conductance in this area. First of all, it was anisotropic. So in some direction, this is the surface of our sandwich. In some direction on this surface, the mobility of charge carriers, the holes, not electrons, the holes, was very high, and at the temperature, at the absolute temperature, 145 Kelvin, high temperature superconductivity was observed. So the question by Bargraev formulated for myself was, what was the reason for high mobility and for this superconductivity? I am a mathematician. So you see, I am able to produce a sort of version of mathematical answer. And this is what I will expose to you now. I am not sure if my answer is sufficient for physicists. But anyway, it was supported by Bargraev, and I am waiting for the Nobel Prize. So now, okay, so actually what I want to expose to you is a model, a reasonably good model to my mind for periodic, physically meaningful periodic lattice. Then I should recall what Biermann told once about periodic lattices. Of course, he knew, and everybody knows in this room, that usually periodic lattices are very well studied in one-dimensional case. In one-dimensional case, to construct the Bloch waves, you just consider the solutions of Cauchy problem and then construct the Bloch waves by linear combination of standard solutions. Then Cauchy problem in two-dimensional case is ill-posed, so you can't go this way in two-dimensional case. And Biermann even told that nobody knows what are Bloch functions in two-dimensional case. So of course he was wrong, because physicists know what are block functions, and they are brave enough to calculate them and happy enough to get right answer. The question is how to get something which may be achieved analytically. So my first aim now is to produce a reasonably soft mathematical model of the two-dimensional periodic lattice. When I say soft, I mean soft in the sense used by Arnold. He explained that the model should contain enough parameters to produce reality, to reproduce reality, but not too many to remain practical. One of my students taught me that if you have 2 parameters, you already can construct an elephant, and if 3, then it will be moving. So I believe that in this case we have at least clear set of parameters. Sorry, I will be jumping. I will be jumping. This is the lattice I wanted to discuss. And the lattice, the drawing of this lattice is in full agreement with what Bagrayev told me about his device. It is a rough sketch of rhomboidal lattice with links containing 2 neighboring periods and some non-trivial family of atoms, silicon or silicon plus borons, on these vertex domains. It is very rough picture. More realistic picture is here. It is 1 period. Actually, it is here. The period is here, so you can imagine that we have few atoms of borons and silicons on the domain, and we have reasonably narrow contacts with neighboring periods. So now, how to construct the Bloch waves? We may use straight the Bloch boundary conditions here. P plus is the projection on a selected subspace of the space L2 of square integrable functions on the bottom sections of contact gamma. So now, if we introduce this boundary condition, we may expect that we will construct the Bloch waves. But we need the Dirichlet-to-Neumann map. My trick is actually the following. We take the rational approximation of the classical Dirichlet-to-Neumann map near Fermi level. So lambda r are several eigenvalues of the Schrödinger operator on the period, which are situated near the Fermi level of the material. So this is the corresponding sum here. Q is formed of residues which are combined of eigenfunctions, of the normal derivatives of eigenfunctions on the bottom sections. Here is the remaining part, which can be also represented in more pleasant form. If you have only one resonance eigenvalue, you may take this term containing actually sum over all possible eigenvalues of my Schrödinger operator on the period. We may calculate the sum just at given eigenvalue lambda r, and then plus small additional correcting terms, which disappears when lambda is approaching to lambda r. So what is my trick now? I consider the Dirichlet-to-Neumann map, but not the whole Dirichlet-to-Neumann map. I take the polar part of it on the temperature interval, maybe only one term, then a constant term which takes into account remaining eigenvalues, plus a correction which is estimated by the difference between by the temperature, this way. So now, of course, this program of calculating of the Bloch waves, which is suggested now, is not so simple numerically, but is still realistic because we have for finite dimensional space E plus, we have only finite linear system, and we have an algebraic determinant condition for the dispersion function lambda of quasi-momentum of two quasi-momenta. We have here two-dimensional lattice, so we have P1, P2, and we find lambda as a function of P1, P2 from this determinant condition. So this is more or less clear computational way. I may recognize honestly that personally I did not pass this computational way. My students tried for very simple examples. They proved that in one-dimensional case nothing new appears exactly what we have in standard Cauchy approach. And I'm directing now to the main problem about silicon boron sandwich. So now let us consider, you see only a part of this picture, but you can easily imagine the remaining part. It is just symmetric with respect to this wall, imaginable wall. So you have a period in the upper layer of the sandwich. You have a similar period below on the lower layer, and you have a connection between upper period and lower period, which is arranged by operator extension procedure. So we have actually the whole lattice consists of quasi one-dimensional lattice in the upper layer, similar quasi one-dimensional lattice in the lower layer, and the connection which is here. You should criticize me immediately, saying that why I assume that each upper period is connected only with the opposite lower period. Of course it is wrong. I should assume that I have a group maybe of 5 periods from the upper layer connecting with corresponding period in the lower layer. But this is not so important for the beginning. Then we may try to solve the corresponding algebraic, finite dimensional algebraic equations. So now you see, we have only one seriously selected parameter. This is the space E plus, which corresponds to the, which defines the connection of neighboring period, and another space E0, which corresponds to the connection of upper period with the lower period, and the parameter beta. This parameter defines actually the rate of interaction of the upper layer with the lower layer. So now, how does it look? It is now it is algebraic. We have here six equations. They form a finite system. Yeah. And then you can introduce the corresponding determinants and represent the determinant condition here in this form. So beta is encoded here. If beta is infinite, then you may cancel the first term and you obtain determinant condition which define the dispersion equation of the upper and lower lattices. If beta is finite, then you should take into account the connection between these two conditions. So now the question is, what sort of phenomena can we observe? The very rough statement is the following. If we have I should draw first the picture. If you have the dispersion equation and the corresponding surface which correspond to the upper layer, if you have similar dispersion equation and the surface which corresponds to the lower layer, then you see that for finite beta you will have some intersection. Now let us take our microscope and observe the line of intersection at some point. Then this is what you will have. Then if beta is large, then the behavior of electrons is quasi-relativistic in this direction, in the direction n. So effective mass in the direction n is quite small. Effective mass is approximately the curvature, inverse curvature of the surface along this channel. Then effective mass is anisotropic, and it is just close to usual conventional effective mass along the channel. So this is what I have shown to Bagraev, and Bagraev told me that practically what he is seeing is not exactly this picture. he sees another picture. And this is a spectral gap which exactly defines or may define the superconductivity. So this gap can be added to the standard Barden-Schiffer, Cooper-Barden-Schiffer spectral gap, increasing the critical temperature. So now I stop here because the rest should be reported to physical conference. I can show some pictures. How much time do I have? 15 minutes. I will lend 10 minutes to my friend Professor Weinberg, and I use 5 minutes to show some physical pictures. Oh, somebody can help me. I don't know how to. Yeah. Yes, I want to close this page and revoke another one. Close it. Yeah, and then open this one. Yeah, thank you so much. Then you see here the pictures which are produced by the team of Bagrayev. And these are exactly where we have common point with Bagrayev. It is about network. Yeah, these are the formulas I already commented. Yeah, this is the picture of double period. And this is about Landau-Zenner effect. What is Landau-Zenner effect? It is exactly the transformation of intersection of terms into quasi-intersection. It was discovered in 30s, and the picture is one-dimensional, and this picture, and the picture I showed before is two-dimensional picture. Now, yeah, and these are experimental pictures. So the experiment showed exactly the anisotropy of mobility and the periodicity of each layer. Then my last comment is about two pictures which are present here. One picture is the anisotropic behavior of the effective mass and mobility. And another picture, it is the initial picture of graphene. Mobility in graphene is usually commented by this picture. And this picture looks strange from my point of view, because the one-dimensional transformation of intersection into quasi-intersection, the one-dimensional sujet of transformation, can be considered from the point of view of catastrophe theory. You may assume that you have a hyperbolic paraboloid, and then consider the sections of it by planes. When you go down, you meet the saddle, and on the saddle you have intersection. And then it is transformed into another intersection. So it is the saddle here we have two branches, and when we move along the parameter beta, beta equal infinity, it is here. If beta changes sign, you may obtain something like this. So it is more or less clear how the transformation, how the small effective mass appears in the sandwich. My question is how this guy, three-dimensional cone, may appear on two-dimensional basement. I don't understand it. When I ask physicists, they claim that everything is okay here. They never have a doubt about this picture. But somehow I'm not physicist, so I still need some clarification here. And I have on my side the prominent book by Arnold, where he proves that for one-dimensional resolution of singularities, which is shown here, everything is okay. But if you try to make the two-dimensional resolution of singularities, you will not be able to obtain these cones. So this is my question. I don't know what do we really have in graphene. All physicists believe that they know. I don't know. I'm not a physicist. Sorry for that. I finished.